What's up, everyone? Today we're talking about supersonic parachutes on the Martian atmosphere. So the paper we're looking at today is the effect of Martian atmosphere on aerodynamic performance of supersonic parachute two-body systems. And you can find this online. It's open access. So what is that title? So first of all, we know it's the Martian atmosphere. We know it's aerodynamic performance, and it's of a supersonic parachute two-body system. So what is the two-body system that we're looking at? So it's going to be the capsule, and then directly behind you have the parachute. So you know how we always see like a drone or something that's descending onto a planet. You have the drone and then the parachute above it, resting its fall. That's what they're looking at in this paper. So in the abstract, they go, both rigid and flexible parachute models are considered. So the rigid model is where you have the parachute is rigid, so it's just this semicircle dome, and then that's connected to the capsule with a rigid bar. And then the flexible parachute is effectively like what you just see regular parachutes. For example, you know, in the movies where you have army paratroopers where the parachute is this really circular round dome like that. The objective of the present study is to investigate the effects of the Martian atmosphere on the unsteady flows produced by these parachute two-body models and the structural behavior of the flexible canopy. So in that, they're talking about how the flow coming off the capsule impacts the parachute's performance. And not only that, you have then the flexible parachute, which is going to then perhaps change its shape. And that's what's called a fluid structure interaction. And that is where you have, when you have an object or a structure, and then it creates some sort of force, and then that force affects the structure. Maybe it changes its shape or changes orientation or something. So that can control it. And then that then changes the aerodynamics because the shape is now different. And so you have this interaction between these two. And that's what they're looking at here with the flexible canopy, because the rigid canopy can't be changed shape. It was found that in the Martian atmosphere, the supersonic rigid parachutes with shorter trailing distances exhibited weaker aerodynamic interactions between the capsule wake and canopy shock, resulting in a smaller pressure distribution on the typical surfaces of the canopy. Okay, so what does that mean? It means that when these canopies were closer to the capsules, so a shorter trailing distance, there was a weaker aerodynamic interaction between the capsule wake, so the wake coming off of the capsule, and then impinging on the canopy shock. So both of these objects, they're obviously attached, but they're also both flying at supersonic speeds. In this, they're going to have a shock on the capsule and also on the canopy. So there are two shocks to consider there, and they can both interact. And there's also the wake of the capsule interacting on the canopy. So why is this important? Why does anyone care about these parachutes? Well, if you want to descend onto Mars in one piece, you kind of need to use this system. There are other systems that you can use, like deceleration and that, but the parachute model has been used a lot and is successful. So that's why understanding what the aerodynamics around the parachute is important, because the more you understand that, the better you can design your parachute, and then also understand what parameters it's built for, so you don't go in too hot, or when you should deploy it, and even what shape and size you should have the parachute. Because if you have a too small parachute, then it's not going to be effective. You're going to crash into Mars. So in the introduction, they go, on July 23rd, 2020, the first Chinese Mars lander, Taiwan-1, was successfully launched to Mars. To date, in successful Mars exploration missions, a supersonic parachute has always been deployed to decelerate the spacecraft during entry, descent, and landing on the Mars' surface. So that's why you need the parachute. And that's the whole point of this field. And then this researcher, Maynard, first conducted an experiment to investigate the aerodynamics characteristics of ribbon parachute models under supersonic conditions, and observed that the drag coefficient of the parachute system depended significantly on the Mach number, canopy porosity, and distance between the forebody and canopy. So that makes sense. So if you have going at a faster Mach number, the drag is going to change. The canopy porosity, so how easy it is for the fluid to go through the canopy, or difficult, that also is going to change how draggy it is. And then also the distance between the forebody and the canopy, so the capsule and the canopy. In other words, how much is the wake that's coming off of the capsule and the shock affecting the capsule, the canopy. In addition, the four-body wake has a marked effect on the drag performance of the parachute system, and that's quite obvious. I mean, pretty much any bluff body system, if you have the wake from one object impinging on another one, which is directly downstream, that's usually going to reduce the drag. That's called slipstream. Now, when you have streamlined bodies, that's often not the case. For example, well, that's sometimes not the case. For example, if you have two wings, so two airfoil sections, and you put them in line, so the flow going over the first one, it goes over the leading edge and the trailing edge and hits the second leading edge and trailing edge. If they're both in line, that's fine, as long as they're not producing lift, and that's decent. Then you're not going to have too much of a wake impinging on the second airfoil if it's designed properly. But if you pitch the first wing, so let's say it's even at, well, let's say you stalled it, so there's a big wake. That wake is now going to impinge on the downstream airfoil, and you're going to have probably a greater drag because now you don't have this nice free stream velocity which is designed for impinging. So having the four-body wake having a marked effect on the drag performance of the parachute system from a bluff body angle, that's pretty obvious. So one thing that they talk about is a canopy breathing instability phenomenon. And what this is it results from it originates from the flow instability around the supersonic parachute, in which canopy bow shock / canopy wake interactions were observed. So what this means is that the shock from the canopy interacts with the capsule wake, and then this creates what's called a canopy breathing instability phenomenon. So there's this transientness to it. So it was also observed in these past research campaigns that an increase in the trailing distance from the capsule and canopy resulted in an increase in the drag coefficient of the system, which, as I mentioned earlier, is to be expected because you have two bluff bodies. So usually, as you put them closer together, the wake of the first bluff body often is very good at reducing the drag of the second bluff body. So the further apart you put them, the less drag there is. A common example of this is in cycling, when you have two cyclists right behind each other and they can go faster, both of them, than if they were just going alone. So it should be noted that to date, most numerical experimental studies have been performed in Earth's atmosphere because a Martian-like atmosphere is too difficult to obtain in wind tunnel tests on the ground. So why does that matter? Why is the Martian atmosphere so important to investigate compared to the Earth's atmosphere? They're both atmospheres. So why do we care? Well, there are a few reasons. One is that if you think about how any object that you send to Mars is going to be falling to Mars, it's going to be going through from a high altitude to a low altitude. And as you descend, the temperature is going to change. The same thing with Earth. As you go higher up, the temperature drops. And we have empirical formula that a few different empirical formulae, some which are very crude, some which are very sophisticated, that will give you an idea as to what the temperature is as you go higher up in Earth's atmosphere. One very crude one, which is somewhat accurate and is a really good just initial idea, is that every 100 meters you go up, you drop in temperature about 1 degree. And Earth's empirical formulae are not the same as Mars's. The temperature is different, and that's going to change the aerodynamics because you have shocks. Another important difference between Earth's atmosphere and Mars's atmosphere is the pressure. It's much lower on Mars. It's about, I think they tested a couple of different types, and there was like a third of the atmosphere's kind of thing, of the pressure. And then another very key difference is the atmosphere's constituents. So on Earth, we know that most of our atmosphere is nitrogen. Then you have quite a bit of oxygen, then a little bit of some trace elements like CO2 and that, a few percent. On Mars, the atmosphere is about 95% CO2, and then you have trace elements from there. So why this is important is because of one particular parameter. For example, something called the specific heat ratio, which is called gamma. We often refer to it as gamma. It's also called the isentropic expansion ratio. Now, what this factor gamma does is it dramatically affects the angles that a shock will come off of a surface. So we actually have a video on our Every Aerodynamics playlist, which shows a supersonic flow going over a ramp, and then you have a shock coming off of it, and that comes at a certain angle. Now, that angle is, among other things, determined by the gamma, the isentropic expansion ratio. So the gamma on Earth is about 1.4, on Mars is 1.3. So these shocks are going to be coming off at different angles. So that's why looking at the difference between Mars's atmosphere and Earth's atmosphere is important for this application. So going further, recently a few numerical investigations on supersonic rigid and flexible parachute systems in a Martian atmosphere attempted to study the complex flow field around parachute systems and their aerodynamic performance. It was observed that the flow mode around the supersonic rigid parachute was basically identical to that in the Earth's atmosphere. So what that means is, effectively, when you have the rigid parachute, so effectively just the bowl which can't change shape and it's connected to the capsule with this rod, that the aerodynamics of that in the Martian atmosphere was the same as Earth. And the standoff distance of the capsule shock and the parachute drag forces were similar to those in air conditions, so Earth's conditions, for the rigid parachute system with different trailing distances. So the standoff distance of the capsule shock, that just means when you have, let's say, the capsule, that's that, and you have a shock coming onto it, so it's traveling this way, how far away from the capsule it is. So those are all very similar to Earth's atmosphere, which means that in the rigid parachute system, there's not a huge effect of the Martian atmosphere on its performance. However, in contrast, the flexible parachute with the same material exhibited different deformation trends and corresponding drag coefficients in a Martian atmosphere than those in the Earth's atmosphere. So the flexible parachute, because you have a different atmosphere and different shocks and wakes and that affects the shape and the size of the flexible parachute, so the deformation. This study aims to investigate the complex flow fields and the aerodynamic interactions around the rigid and flexible parachutes numerically and comprehensively to understand the fabric dynamics of flexible parachutes in a Martian atmosphere. So this is a fluid structure interaction problem. So they go through the different models, and they go through the rigid model, which is the solid rod connecting to the solid canopy. Then the flexible model is similar to a real parachute, as we mentioned. Now, when they investigated this numerically, they used CFD. I don't want to go through the entire setup because a lot of it is pretty normal. A couple of parameters that are interesting is one, the Carrot number is less than 1. So the Carrot number is the time, how far a particle will travel in a given time. So if you have, let's say, a time step of 0.1, a very large time step usually, that if that travels through, let's say, 10 cells, that's really high. You want it to be 1 or less. Certain parameters you can get away with higher. And the reason why is because the less cells that this particular particle will travel through, the more accurate your simulations will end up being usually. Now, just on that, we offer CFD courses. So if you want to get better at CFD, check them out, link in the description. Now, the other parameter for their CFD that was interesting is that this is a supersonic flow, as I mentioned. It's Mach 2. Now that's pretty fast. I can throw a ball that fast, so it's no big deal. I'm pretty awesome, but it's pretty fast for most people. And in this flow, they had no turbulence model was applied in the present calculations of the rigid or flexible cases, because in the previous studies on both rigid and flexible parachute systems, numerical results obtained by the laminar simulations were in good agreement with the experimental data. So this is if you're not expecting it, this is a very interesting result. And the reason why is because when you're learning about aerodynamics, you usually start with subsonic flow, and often very subsonic. So you're looking at Reynolds numbers of 5,000, 10,000, 100,000, maybe 10 million at most, maybe, or 100 million. And what we're taught is that in these subsonic flows, the Reynolds number, which is a good indication of turbulence, the higher the velocity, the higher the turbulence is going to be, and the higher the Reynolds number in that. Now, So that means that if you want to get a turbulent flow, it's really just a matter of increasing the velocity. You can also increase other parameters like the density or the characteristic length and that. But one way is just you increase the velocity. So we think that if you want to get a turbulent flow, just go much higher. Now, this is a Mach 2 flow. It's a really fast flow. And they're not using turbulence modeling. And they can get away with laminar simulations. So that's a bit counterintuitive. And that's because we now cross over the sonic threshold. And from there, we actually get often suppression of turbulent features. So you don't need to involve the turbulence modeling side of it. So that's a really interesting difference between subsonic and supersonic flows. So going on, they look at the structure calculations. So as I mentioned, they were looking at the sort of structure interaction, how the aerodynamics of this structure affects the structure and vice versa. To do that, they're using something called a mass spring damper model. Now, if you what a mass spring damper system is effectively any structure you can effectively model as a mass spring and damper system. Now, you might have a lot of masses, a lot of springs, and a lot of dampers, but generally speaking, you can just reduce it to these three parameters. So what are they? The mass is, so let's say I have this object here. It weighs a certain amount. Now, I can reduce this mass to just a point. So let's say it weighs 100 grams and the center of gravity is right here. I'm going to reduce it to that mass. The spring, and the mass is what really holds a lot of the inertia. So for example, let's think of a pendulum. When you have a pendulum swinging, you drop it and then it will swing down and go back up and keep going. And then over time, through mechanical losses and a bit of aerodynamic resistance, it will come to center. But the reason why it's swinging is due to the mass. It has this inertia that wants to keep going, and you can go from potential energy to kinetic energy and back to potential and back around. So that's one part of the system. Then you have springs. So you have the mass is connected to a spring, and this affects how much of something will vibrate, for example. Then on top of that, you have the damper. So the damper acts as exactly that. It damps any motion. So that's the idea of a damper. So like, for example, if you have friction, that will then be grouped into the damper parameter. So now you can model a system as a spring damper. And that's what they used for these parachutes, particularly the flexible one. And in the mass spring damper model, the canopy surface was considered as an assembly of mass nodes attached to springs and dampers. So this entire canopy was now discretized effectively into all these tiny point masses, and each one of these point masses had springs between them and dampers, so that when they move, that energy will then get imparted to another one through this spring system, and then there'll be a bit of damping, so maybe it will resist that motion a little bit, and so on and so on. And all these nodes get affected. So now to the results. First, they looked at the rigid parachute cases. In previous numerical simulations of rigid parachute models under wind tunnel conditions, so air conditions, Earth's conditions, it was found that the most significant oscillation flow mode, the pulsation mode, occurs around the supersonic parachute two-body system with a short trailing distance, where the shock wave ahead of the capsule exhibits a hemispherical shape. So what does that mean? They said that the most significant oscillation mode occurred when there was a short distance between the capsule and the shock and the parachute. And this is where the shock wave ahead of the capsule exhibited a hemispherical shape, so it's sort of like this dome shape. It was observed that the vortex ring at the foot of the shock wave ahead of the canopy and the complex capsule wake canopy shock and the capsule shock canopy shock interactions work together to drive the pulsation flow fields around the parachute two-body system. So what does that mean? There's a lot in there. So the first thing, it was observed that the vortex ring. So what is a vortex ring? Now, if you don't know what a vortex ring is, it's probably because you do know what it is. You just didn't realize that that's what you were seeing when you saw it. And the quintessential vortex ring is, when someone blows a smoke ring. what this is effectively just a circle, and then the fluid in that circle is now, a ring, is now rotating around about the axis that's tangential to that ring at every point. So let's say you have a ring like this at this point where the slope of the ring is like that, the tangent's obviously like that, and then the flow's going around it. So that's a vortex ring. And there's a vortex ring that occurs at the foot of the shock wave ahead of the canopy. So the ahead of the canopy shock. And the interaction between this and the capsule wake canopy shock interaction, so the wake of the capsule interacting with the canopy shock, and then the capsule shock interacting with the canopy shock. So these two shock waves interacting, all of this together drives this pulsating flow field around the parachute two-body system. So this constantly changing flow field. The pulsation flow mode exists in both the Earth and Martian atmospheres. However, it can be seen that the capsule shock occurs closer to the capsule and becomes thinner in the Martian atmosphere. So what does that mean? So the capsule shock, remember how I talked about the standoff distance between an object, any object, it can be the capsule, it can be the canopy, whatever, and then the shock. That distance reduces on Mars, that between those two, and the shock itself becomes thinner. And this is a function of its atmosphere. What's more, the aerodynamic interactions in Martian atmosphere conditions become weaker, which causes the pressure distribution on the canopy's inner surface becomes much smaller. So that's interesting. All these aerodynamic interactions, as I mentioned before, between the vortex ring and then the canopy shock and the capsule wake and the canopy shock and the capsule shock, they'll become weaker. In previous studies under the Earth's atmosphere, as the trailing distance increases to x on d equals 10. So what is x on d? X on d is the distance between the capsule and the canopy divided by the diameter of the capsule. So this is a way of non-dimensionalizing this distance. And when this was 10, and remember this is for the rigid case, only the capsule wake interacts with the canopy shock. So that's interesting. So the canopy shock does not interact with the capsule shock. Whereas before, when the distance was shorter, you not only had the vortex ring and then all these shocks and wakes all interacting with each other. So when you put these two parts further away, it's only the wake of the capsule and then the shock of the canopy interacting together, which makes sense because the further away you move things, the less interaction you usually get. The interaction between the capsule shock and the canopy shock seems to disappear because of the larger distance between the capsule and the canopy. The unsteady flow mode in the Martian atmosphere is consistent with that in the Earth's atmosphere. Thus, there are small differences in the pressure distributions on the inner surface of the canopy under different atmospheres. Consequently, the Martian atmosphere has a greater effect on the performance of supersonic parachutes with shorter trailing distances. So the Martian atmosphere, between the Martian atmosphere and the Earth's atmosphere, when you have a short distance between the capsule and the canopy, that's when you're going to get greater effects between these two different environments. So that was the rigid parachute. Now onto the flexible parachute. And to start off with, they looked at this original canopy material. So they had this original canopy material that they had been investigating before. And in previous studies of flexible canopies with the same material as assumed above, it was observed that when the parachute system was x on d equals 7.13, so it's closer together than 10, was placed in the Earth's atmosphere, the shock ahead of the flexible canopy moved upstream of the canopy mouth and interacted with the narrow wake of the capsule. Now that's really cool. So when you reduce the distance between the capsule and the canopy, the shock on the canopy moves upstream and interacts more with the wake. So it's not just that you have the wake closer to the shock actually moves upstream as well. So that's really, really cool. When x on d increased to 10, so it got further away, the distance between these two objects, a similar unsteady flow mode and shape change of the canopy was observed as shown in figure 5. So all this is showing is that there's quite a bit of reduction in the wake interaction. It should be noted that in the unsteady flow mode, the strong flow instability generates significant unsteadiness in the drag force, which is computed from the pressure difference between the inside and outside of the canopy. So that's to be expected as well. You know, if you have unsteady flow aerodynamics coming in, you're going to affect the aerodynamics of this object, and the drag is going to change accordingly. Now, just at this point, I want to talk about the drag coefficient and how they calculate it, because it's pretty interesting how they do it. So we know how regular drag coefficients are calculated. It's usually just, I can see that good. CD, the drag coefficient, equals FD, the drag force, divided by the Q, the dynamic pressure, times by S, the surface area, or the frontal area for the drag. So Q is the dynamic pressure, and that equals half rho v squared. So half times the density times by the velocity squared. Now, that's how you do it in subsonic. So instead of this equation where Q is half rho v squared, Q now becomes, they calculate it with this equation. So Q equals gamma, which was the specific heat ratios I was talking about, also the isentropic expansion ratio, divided by 2 times by the free stream pressure times by the free stream Mach number squared. So this point here is the difference and the pressure. So that's an interesting way of calculating the drag coefficient for supersonic objects that differs to our subsonic way of calculating it. And just here, I also want to pause and talk about the atmosphere Hawk. So this is an instrument that we made. It accurately measures the temperature, barometric pressure, and humidity in your system, so your experiments or your real-life measurements. And the reason why they're important is because the density is greatly affected by those. If you're not taking account of these parameters, the density on a regular day can fluctuate easily 2 or 3%, and you don't know about it. That then introduces errors in your system, in your results, and you now have to sort of grapple with that, and you don't know what's going on. So you're going to get a lot of results that are not lining up, a lot of conclusions that may not be the case. So make sure to pick up one of these. It gets rid of all your problems when it comes to that, and it's really easy to use. It just plugs in via USB. Link in the description. So going back to the flexible parachute case, we covered the drag that it's looking at, and now we're looking at how the distance between the capsule and the canopy affect aerodynamics. So in contrast, when the parachute system with X on D equals 7.13, so the canopy is closer to the capsule, when this was placed in the Martian atmosphere, the aerodynamic interaction of the capsule open wake and the canopy shock moved to the edge of the canopy, and the canopy shock became much weaker. So that's interesting. When you put the two closer together, the canopy shock got weaker, which is often a good thing. This resulted in a much smaller drag coefficient than in the air condition. So that's not a good thing. So in this case, it reduces the drag, and the idea of the parachute is that you want to reduce the drag. You want to increase the drag to reduce your descent speed. Note that the canopy shape was almost unchanged in the Martian atmosphere. As the trailing distance was increased to X on D equal 10, so it gets further away now, in the Martian atmosphere, a similar unsteady flow mode to that in the Earth's atmosphere was observed. However, the canopy shape was almost unchanged. So this is something that I had a problem with. They said this does not conform to the real world, although the unchanged canopy resulted in a larger drag coefficient than in other cases. What they were concerned about was that the canopy should have changed shape, so when you have a shock on it and all this interaction. So note that the performance of the flexible canopy with X on D equals 7.13 and 10 in the Martian atmosphere is similar to the performance of the rigid canopy in the Earth's atmosphere, including the unsteady flow modes and almost unchanged canopy shape. So the flexible canopy is acting like on Mars, acting like the rigid canopy on Earth's atmosphere. And this is the original material of this parachute. Consequently, there is a large difference in the performance of the same canopy material in different atmospheres. So again, if you were to test this canopy on Earth, the results that you get from it are not necessarily going to translate to Mars, and that's often a problem. A suitable canopy material from the Martian atmosphere will be investigated in the following section. So this is where they come up with a new material now. So this new canopy material, a more flexible canopy material was designed, i.e. a lower Young's modulus, which is also means a lower spring constant in the mass spring damper system and a lower damping coefficient. So what is a Young's modulus? It's in a nutshell, it's effectively how much an object will shrink or expand when you apply force to it or pull it apart. So what the formula is the stress divided by the strain. So how much force you're pulling away, and then how much that object will expand, or vice versa. So they're looking at something which has a lower Young's modulus, which means that it's not going to deform as much. The newly designed flexible parachute model was numerically applied to the flexible parachute with a trailing distance of 10. As a result, the capture wake became closed. Aerodynamic interaction occurred between the capsule narrow wake and the canopy shock, and a similar change in the canopy shape as that in the Earth condition was observed. So what this means is now with this lower Young's modulus, the Young's modulus the lower Young's modulus, now the canopy in the Mars conditions was also the same, the differences in this deformation as Earth's conditions. Consequently, the drag coefficients of the new flexible canopy in the Martian atmosphere are similar to those in the Earth's atmosphere. However, it should be noted that the amplitude of the fluctuation in the drag coefficient is much larger, which indicates that the effects of the flow stability related to the aerodynamic interaction between the capture wake and canopy shock is predominant, and further improvement of the canopy fabric flexibility is still needed. Okay, so before I mentioned, I think I said that the Young's modulus was, like I said, if you have a lower Young's modulus and you apply the same force, you get a lower deformation. It's the other way around. Sorry, I think I forgot to mention that. I said it the wrong way. So anyway, with this, what I was saying was that they need a more flexible fabric to more accurately replicate the Martian effects with the Earth's effects. So conclusions. In the Martian atmosphere, the unsteady flow modes around the supersonic rigid and flexible parachute two-body system with larger trailing distance are identical to those in the Earth's atmosphere. However, the aerodynamic interaction around the parachute with short trailing distances became weaker, and the pressures on the typical surfaces on the parachute system decreased in the Martian's atmosphere. So that's a difference that they were looking into. The Martian atmosphere has a significant effect on the aerodynamic performance of the flexible parachute system. Owing to the low density and pressure, the flow modes around the flexible parachutes with X on D equals 7.13 and 10, and the same original canopy material, are similar to those of the rigid models under the air conditions in the wind tunnel, and an unchanged canopy shape is observed. So that's something that they weren't that happy with, because now they can't, the results on Earth from this flexible parachute is not transferable to Mars. So finally, under Martian atmospheric conditions, a reasonable canopy material was specially considered, and a smaller Young's modulus and damping coefficient of the canopy material were defined for the design of the canopy to improve its flexible ability. It was also indicated that the drag performance was significantly affected by the two key factors, flow stability and periodic change in canopy shape. So that's an expected outcome as well. So that's the end of the paper. So how much would I rate this paper? I'm going to give this 8.5 Jeff Goldblums out of our 10 Jeff Goldblum scale that we've used before. And the reason why is because I prefer Earth to Mars. Earth is much better. There, I said it. Anyway, so that's the end of this podcast. Make sure to like and subscribe. Check out the Atmosphere Hawk, link in the description. Check out our courses on CFD, experiments, and theory to make you a better aerodynamicist. And big news, our International Aerodynamic Conference is on. It's in October. Make sure to register. The link is in the description. And I'll see you in the next podcast.